when you had x cubed times x to the 5th, what did that equal? X to the 8th. Same base, different exponents. You add. Okay. You also had stuff where you had x squared to the 6th. Power to power, what did you do?
Add.
Multiply. Very good. You multiply and get x to the 12th. When we had stuff where it was x to the 8th over x to the 11th, what did we do?
Played war.
We played war, and we would figure out which one wins. Who wins?
11.
The 11, so what goes in the numerator then?
3.
1. Okay. We did that. We also did this. When something isn't happy, where are they happy?
In the denominator.
Is that
11?
Yes.
Is that
Oh,
And if they were unhappy in the denominator,
happy in the numerator.
then they're happy in the numerator. All of these properties still hold true with fractions. That's it. That's 7-2. To start with.
No, start.
For example,
No.
3 to the 1/2 times 3 to the 3/2. Those two have the exact same base. Do you agree?
Yes.
Yeah.
So you add them.
What's 1/2 plus 3/2?
2.
4/2, otherwise known as 2. So my answer here would be 3 squared, which is 9.
Wait, so you don't have to multiply the 3s?
Did you multiply the x's when it was x squared times x to the 5th?
No, that is because it was x though.
Treated the same way? These are treated the exact same way. Same base, different exponents. When you're multiplying, you're just adding your exponents. Okay? Exact same property happens when we had power to power. If I have 4 to the 3/2 squared, power to power. Which is? So you get 4 cubed.
No. What's happening?
What's 3/2 times 2? 3.
What?
Bless you. You have to know how to work with fractions, guys. 3 over 2 times 2 is 3.
Oh, wow. I was thinking something else.
I'm going to tell you right now, you won't get calculators for a lot of this, so you got to know how to work with fractions. Same deal here. When you have two things raised to the same power, it's a matter of distributing the property to both parts. It works the exact same way with fractional exponents. If I have 9 times 4 to the 1/2 power, well, that means it's 9 to the half times 4 to the half. I heard someone say it, otherwise known as
3 times 2. What?
Oh, man.
what's the square root of 9?
3.
And what's the square root of 4?
2.
3 times 2 is 6. Remember, you're using the order of operations here to simplify these things through.
Didn't I already do it?
It also works, yes, because the grouping symbol. Oh no, we did this earlier.
It's 1 over 25.
So it's 1 over 25 to the half power, which is 1 over the square root of 25, which is 1. Same deal here. Same base, different exponents. When you are dividing, you have to start thinking about who wins the game of war. 5 halves or 1 half? 5 halves. So what's 5 halves minus a half? 4 halves, which is 2. So I get 6 squared, which is 6. Okay. And then last but not least, the distributive property with the fraction. Same basic idea here. You have 8 over 27 to the 3rd power. Now, what did the 3rd power mean again? Cube root, very good. So this is the exact same thing as saying the cube root of 8. Oh, very good. The cube root of 27, which is 2/3. All right. Excuse me. These properties, none of this stuff had changed from earlier when we worked with the exponents the first time around. They just get a little bit nastier because of the fractions. It's exciting. Okay? Which means we have to remember how to find quick common denominators. 5 to the 1/2 times 5 to the 4th. Well, let's give you the quick common denominator between a half and a fourth. Fourth. So 5 to the 1/2, you'll be able to do this in your head, should be 2/4. Well, you get 5 to the 3/4. And for right now, we're going to leave our answers, if they give us exponents, you can leave it in exponent form. If they give us radicals, we'll leave it in radical form. Is that kind of a generic rule for it? Okay. Seven over 7 1/3. Who wins the game of war? The top, because what's the exponent in the top? It's a 1. But I'm going to not use it as 1, I'm going to write it as
3/3.
which is still 1. See what I did there, Miss Bob? You kind of like, you had the worry face for a second.
So is
All right.
it 7 2/3?
And you just leave it. Okay? Take these guys to the next one. Twelve to the third, 4 to the third. Do I have the same bases here?
No.
No. So is there really anything I can do here?
Maybe.
Not right now.
Not at the moment, no.
So let's do this. Let's do the power to power. And then I'm going to show you what happens when you rewrite. When I do the power to power here, we're going to get 12 to the 2/3 over 4 to the 2/3. Does everybody agree on that? The power to power. No. Now, is this the same thing as saying
Yes.
what's 12 over 4?
3.
And there you go. What happens a lot of times with these things, and I could have done that up front, because 12 to the third over 4 to the third, isn't that the same thing as saying 12 over 4 and take the cube root? It's the same thing. But what I like to do a lot of times is use the power, the rules prior to doing any simplifying. That way we don't make too many dumb mistakes. This way, when you have a fraction like that, and you have that same exponent, remember, you can use the reverse of the distributive property. So it's like, if I do that, 2/3 squared would be 4 over 9. You agree on that?
Yes.
Well, that's the same thing saying 2 squared over 3 squared. It's kind of working itself backwards and forward, just using the properties. That's what I'm getting at here. Do the little simplification within if you can. Now, in this next one, if I'm looking at 8 to the half power and 5 to the third power, can I multiply those two together? I cannot because they're not the same exponent. So the bases won't work with that. So what I need to do here is distribute my power, the power to power rule. So I wind up with 8 to the 1/2 squared, so that gives me 8 times 5 to the 2/3. That's all I can do with that. That's all I can do with that. Because when I do the distributed property, I get power to power for the 1/2 squared. Well, 1/2 times 2 is 1. And then 1/3 times 2 is 2/3. This is kind of the same idea of looking at a root as 8 cube root of 5 squared. Sir?
So like for the 8 to 1/2 power, you only multiply the 2 on the outside to the numerator?
Yes, because when you're multiplying fractions, you're multiplying straight across.
Okay.
And it just so happened, that's just kind of the downfall
I
of,
got it.
they write it as kind of a slashy fraction. So it's 1/2 times 2 over 1, which is 2 over 2, which is 1.
Okay.
That's what they're doing long form, if you will. Yeah, Kobe.
When we like get an equation like when we get like a problem like that, or can we just leave it as 5 to 2/3?
Yes, I was just showing another way to write it.
Will we ever have to do that?
But to rewrite it out as the root,
Yeah.
if it asks you to write it as an nth root, you'd write it as an nth root. If it says exponent, write it as an exponent. But generally speaking, if you start with an exponent, you'll end in an exponent. And then lastly, I have 2 to the 4th power times 3 to the 4th power. All raised to the -4th. Now, if you look at this, if I distribute through, gives me see how it's faster to distribute in this case instead of trying to multiply stuff out? Because 4 to the -4th is -1 for both of them. So are these guys happy? Yes, ma'am. Oh, yeah, I'm not done yet. Is that what you're getting at?
I just put them in the denominator first.
That's fine. You get 1/6. Okay? And that's perfectly fine. There's nothing wrong with you doing that step first. Okay? Same idea with radicals. The same idea with radicals. And you probably have done this. I know you've done this because I know that each and every one of you guys has simplified the square root of 8 before. What's the perfect square that's hiding in the square root of 8? 4. You guys broke this down before as the square root of 8, as the square root of 4 times 2, which was the square root of 4 times the square root of 2, which gave you 2 root 2. You've done this property before, you just didn't know that's what you were doing. Okay? What? So this shouldn't look that weird. Right. Same idea with this. When you have a square root, now I was pretty lenient on that number 2 where you had take the square root of 1/3. We hadn't done a single problem yet in this class about rationalizing the denominator, but you guys have done that in the past. From here, after today, we will have to make sure we're always rationalizing denominators. This is where it's going to come into play today. For example, if we go back to that number 2, you had the square root of 1/3. That was the exact same thing as saying the square root of 1 over the square root of 3, which was 1/√3. From there, if you recall from last year, you guys had to rationalize your denominator because is it polite to have a root in the denominator? No. You had to multiply it by √3/√3. You multiplied it by some factor of 1. Same idea when we did we did some radical stuff with quadratics and the imaginaries. We didn't want to have imaginaries. We did all that same, we rationalized. So we multiplied by root 3 over root 3, because this is equal to 1, and you got root 3 over 3. Same idea. It's using these properties that allows you to do that. Well, not only were we going to rationalize square roots, we're going to rationalize cube roots.
No.
Whoa. We're going to do that as well. It's exciting. Okay? So let's take a look at these two. When I have the cube root of 4 times the cube root of 16, that's the exact same thing as saying the cube root of 64. Convenient, isn't it? Because now, what's the cube root of 64? 4. Okay. Using this one, same deal. Notice how they have the exact same end root. It's the 4th root of 162 divided by the 4th root of 2, which means I can encompass the entire fraction as the 4th root. So I have the 4th root of 162 over 2, which is the 4th root of 81. Gee, what do you think 4 numbers are that you multiply together that are the same number that get you 81? It's using these properties going forward and backwards.
Yeah, it would be plus minus 3.
It'll only be plus minus 3 if we're doing the over equation, like in the equal stuff. When you're dealing with these things, we're going to keep it with whatever set. Plus, you keep it with the sign that they give you. If they give you a 4th root of negative 162, you can say, no. But if they give you the cube root of negative 64, then you can do that. Because the idea is that the odd exponent. So hopefully this isn't looking so horribly bad, scary yet.
Oh, yeah.
I mean, not bad.
Yeah, next slide.
Probably gonna
Yeah, for real, that's the line.
Let's
Oh, God.
let's simplify some of these and see how what we remember.
I don't like
Okay.
this idea.
Oops. We know what the square root of 12 is, if you simplify that out, right? That's a common one that you guys probably saw a ton of last year in geometry, second semester. 2 root 3, very good. We know that the square root of 12 is 2 root 3. But what are we going to do when we start getting cubes? When you're looking for perfect squares, you guys are fairly decent at that. You're looking to see if the number underneath the radical is divisible by a perfect square. You're checking to see, is it divisible by 4, 9, 16, 25, and so on. But when you're worrying about a perfect cube, you have to start thinking about in terms of 8, 27, 64, and so on, 125. Okay? You'll pick up on this real fast. 2 cubed is 8. 3 cubed, 27.
I know much squares.
Well, how you better learn them is 6, because you won't get calculators on most of this stuff. It gets real big real quick. So as you're starting to look at some of these values, if you have cube root of 54, well, the only ones that'll work are going to be anything that's smaller than 64. It has to be either 27 or 8 if I'm going to be able to simplify that. So is 54 divisible by 27? It is. So we can break this apart just like you would radical when you did square roots. It's the cube root of 27 times the cube root of 2. But what's the cube root of 27? 3. So my final answer would be 3 cube root 2. Okay. You're simplifying the radical, in this case an nth root, by looking for a perfect nth value. Okay. The rationalizing is where things get interesting.
I need to go home.
Rationalizing. When I have the fifth root of 3/4, what I'm going to do is I'm going to split that root into both, put it in both the numerator and the denominator. Very similar to what we did when we had the square root of 1/3. Square root of 1 over the square root of 3. We do the same thing. You be okay with that? Okay. Now, we don't like roots in the denominator. So we have to figure out some way to get rid of it, which means we have to rationalize it. Now, when we did this before, when we had 1 over the square root of 3, I'm going to show you what exactly you did here. Isn't this the same as 3 to the 1/2?
Yeah, sure.
We can go with that.
Now, when you rationalize it, you multiply by the top and bottom by the square root of 3. Do you agree? The square root of 3 is the same thing as 3 to the 1/2, right?
Yes.
Isn't the same base when you're multiplying? What did you do to the exponents? You add them. What's 1/2 plus 1/2? 1. So your denominator here became 3 to the first power, and this stuff up top became, 1 times 3 to the half power, which gave you the square root of 3 over 3. You're using these properties of exponents to add the fractions to get 1. What happens here when you have this fifth root of 4, this is the same thing as saying 4 to the 1/5. What do you have to add to 1/5 to make it 1? 4/5. Because isn't that 1? All you're doing is you're multiplying it by some shape changer, by some factor of 1 that'll allow you to get rid of the root in the denominator. Because now that you multiply across, you have 4 to the 1/5 times 4 to the 4/5, same base, different exponents, add them. What's 1/5 plus 4/5? 5/5, otherwise known as 1. I get 4 there. Okay. Numerator, I still have 3 to the 1/5. But think about what I have up top now. I have 2 different bases. I have 2 different exponents. Is that going to help me with anything? Probably not. So I'm just going to rewrite it. I'm going to get the fifth root of 3 times the fifth root of 4 to the 4th, all over 4.
That's it.
And that's it. If you're wondering, can you keep it in with the fraction?
No.
Usually when because in this problem here, see how we started with the root? So we're going to end in the root. Okay? Is that what you're asking, Lucia? What were you asking that?
Nothing.
Oh, go ahead. Please. Right, please. This is where things can get nutty. I'm not going to lie to you. All you're trying to do is create 1 in the denominator, and I highly suggest switching from root to fraction because it's easier to add the fraction than it is to try to visualize what you got to do here. That's just my own personal opinion. Okay? I think it's always a little bit cleaner to go that route. Okay. Trying to look? Before we run out of time here. Let's do cube root 2/3. Let's make it easy. Again, I'm going to split apart the root. I'm going to rewrite it real quick in terms of fractional exponent, because it's a little bit easier to work with the fractional exponent. In doing so, I get 2 to the 1/3 over 3 to the 1/3. What do you add to a third to make it 1? 2/3. So I'm going to multiply top and bottom by 3 to the 2/3. What's my exponent now for the denominator? 1. My numerator would be, back again, cube root of 2 times the cube root of 3 squared.
So will you ever be able to simplify the top?
It depends on the problem. I'm just making stuff up off the top of my head. Okay. It really does depend on the problem. We'll worry about more of this as far as what do you call it, variables and stuff are concerned tomorrow. I just want to get you guys started on these exponent rules and jumps. So let's see. This is 7. Almost over the right page. Let's do this. This is 7.2. This is page 411, number 22 to 48 evens. Okay? That's about as far as we'll go through those today, and then we'll see what we wind up with tomorrow. All right?
Right.
We'll build into this tomorrow. We'll talk about adding, subtracting, and then throwing in the variables.
Are you giving us homework tomorrow?
It's a day that ends in Y, isn't it?
That is true. It is.
We have all these for a reason.
Yeah, I'll email my ideas. I have it on the website.
There's like a whole other.
I'll leave when we